Okay, thank you for your patience. Um, okay, well, welcome all for the symposium. I'm really excited to have this event here. And we're also broadcasting live on YouTube, and it's gonna be there unless someone says something they don't want to stay there. We still can edit it. Just wanted to let the speakers know. But it's the idea is for the video to be there as well. Um, so the whole goal for today's event, well, it's going to be today and tomorrow, is to celebrate Latinx voices in STEM. And the goals are very simple. So we just want to increase visibility for Latinx community in campus here at UW-Madison. I'm sorry, I should have introduced myself. So my name is Claudia Solis-Lemus. I'm an assistant professor here at the Wisconsin Institute for Discovery and the Department of Plant Pathology. And actually, I'm sorry, let me go back. I wanted to thank the support from Wisely and CALS and the Wisconsin Institute for Discovery, because without their help and money, we wouldn't be able to have this event. So thank you. And like I said, so the goal is very simple. We just want to increase visibility of the Latinx community in campus and to build connections within the community, and also for people that do not identify as Latinx but want to get to meet people from it. We also want to encourage those connections. And lastly, learn something new about Latin America. So if you just meet someone new, learn about someone's research that you didn't know before, or just learn a new fact about Latin America, then that is considered a success for this symposium. And for this first part, I just wanted to talk a little bit about some statistics. These are more focused on the Latinos populations in the US. I want to thank Luis Macias for sharing these resources with me. And basically, this population is growing from the 70s to 2022, where it reaches 63 million people that identify as Hispanic living in the US. And what's interesting is that in some states, it actually is becoming the largest racial group. For example, in California, in 2014, there was this shift where Latinos or Hispanics became the largest group. We can see it here on the first slide. I should actually use my cursor. Oh, no, we cannot see my cursor. Wait. No, we cannot see my cursor. Okay, so in the first slide, you can see the cross happened in 2014, where now Hispanic became the largest group, and white, which was the second, is the second group. And in Texas, for example, that shift happened in 2022. So the population is growing as becoming major racial group in certain states. And also the composition of this group can be diverse or not as diverse. For example, here are just two areas of the US for comparison. So there is the Northeast that is a lot more diverse with different groups from Mexican, Puerto Rican, Salvadoran, Dominican, Guatemalan, Ecuadorian, and other groups. So there's a lot more diversity in this region. If you look at the percentages, compare, for example, with the Midwest, where those that identify as Latinos, the majority of them come from Mexican heritage. And if you go to these, actually I should have said that, so all of this is coming from the Pew Research Center, so there are the survey. If you look at that, they actually have also these percentages for other regions in the US. So it is a group that is growing, but is diverse in different parts of the US. And the growth is coming from birth, people being born and identifying as Latinos, not so much from immigration. So when we compare to the 70s, the bars were smaller, but also very similar, immigration and births. But now we go to 2020, 2022, the birth is a much bigger bar compared to the actual immigration. And what's interesting that is also shifting is the speaking Spanish versus speaking English. There's also this other shift of people that speak Spanish at home that's actually this proportion is smaller compared to those that speak English, and I guess that also makes sense from those that are born here, and are integrating more into the U.S. culture. And there is a difference between the ones that are born here in the U.S. that do speak less Spanish at home compared to those that were foreign born. So those that were born somewhere else and migrated to the U.S., they continue to speak Spanish at home. So that I thought that was an interesting shift as well. And this is kind of like thinking of the US as a whole. If we focus on college populations, the student body is a lot more diverse, but the faculty body still doesn't catch up to that. So I'm gonna try to guide you through this plot. There's a lot happening here. So these are racial, oh, I wish I could have my cursor. There's a line there, and the races that are above the line, faculties overrepresenting the student population. So for example, for whites, there is 55% of undergraduates that identify as white, and 76% of faculty identify as white. So there is a bigger proportion of faculty compared to the student population that identify as white. Similar for Asian, so there is a 7% of undergraduate students that identify as Asian, and there is an 11% of faculty that identifies as Asian. So those two races, the students are overrepresented by faculty. But if we look below the line, if we focus just on the Hispanic population, for example, there's a 20% of undergraduate students that identify as Hispanic, but just 5% of faculty identify as Hispanic. So there is this gap where the faculty proportions do not really align with the student proportions. And some of the hypotheses for low performance of this population has to do, on one side, the lack of role models, but also the lack of having someone to reach out to if you're struggling, right? So I think that there's gotta be this, we wanna close this gap so that the faculty represents the proportions that we have in the student body. This is a survey. This is not the UW-Madison, I should say. This is a survey that was done over several colleges in the US. And if we look not just at college, but like STEM workforce, there is also a minority of people that identify Hispanic. Here, the ones in the middle, there was 11% in 2011, and then 15% in 2021, so there's a tiny growth, but still smaller proportion. And if we focus on degree recipients now on the right, the brownish bar is the one that corresponds to the ones that identify Hispanic or Latino. And what's interesting is that for the bachelor degree, there are 17% that identify as Latino. That shrinks to 13% for master degree and shrinks more, 9% for doctoral degree. If we compare that to Asian, for example, there is a consistent percentage. So there's 12% for bachelor, 12% for master, 11% for doctoral. So it is a minority, but the percentage is not shrinking. Whereas for the Latino population, as you go further and higher master, PhD, the percentage shrinks. Yeah. So that's also something that could be related to the faculty as well, or there are many hypotheses. I'm not gonna venture to give hypotheses, but just presenting the statistics as something that we want to pay attention to as a society, and as a university. And then lastly, these are just by degree, by field. If we compare the statistics on agricultural and biological sciences, engineers, social behavioral sciences are the ones that have the highest percentage, and the lowest are physical and mathematics and computer science. Both, and this is the one on the left is bachelor, and the one on the right is master and PhD. So this is more just as a landscape to say, yeah, there is a growing population in the US that identifies as Hispanic, but that has to permeate into universities, both in the student body and also at the faculty level as well, so that is well represented in college and in STEM workforce. And I wanted to end with a positive statistics that I found of Latin America, and that there has been this shift now where there are more women that are reaching higher levels of master's and doctoral in Latin America compared to men, which I thought was really interesting and positive. So I wanted to end with a positive statistic, so that is exciting. And I wanted to find, I also read that there's also the proportion of students that go to STEM field is also increasing in Latin America, which is very exciting as well. I couldn't find the plot, so I will find the sources. So I think that's also something that is important to bring up. Okay, so the point was just to tell you some statistics about the population and what we hopefully should pay attention, not just as a society, but as a university, into our culture. And before I pass it on to the speakers for today, I want to just highlight what we're gonna do today. Like I said, we're just here to celebrate diversity and specifically our Latinx community in the university. We're going to have 6 talks by faculty that identify as Latinos, Latinas, Latines here at UW-Madison. And then we're going to have a reception that's going to have food. It's not Latin food, I'm sorry, but it's free food. So hopefully that's still good. There are some rules about the type of food that we can bring. But it's food, and then we're also going to have some music. There is a Spotify playlist that was actually crowdsourced by the Latinx community in campus. So anybody that identified could put songs, actually 4 hours long. We only have 1 hour for the reception. But if you want, you can keep putting songs, and it will also always be there for anyone that wants to check it out. And we also have some posters by grad students and postdocs that wanted to bring them. The QR code for the schedule and for the Spotify list and for the YouTube, they are all on the poster here. If you want to check it out later, feel free to post anything. I put here the Instagram and Twitter tags for both COWS and the Wisconsin Institute for Discovery that have, like I say, supported this event. And for tomorrow, we're going to have at the 8 a.m., I know it's early, but we're going to have coffee and some cookies, and we're going to be playing a game that in Mexico we call it Basta, which is that they give you a letter of the alphabet, and you have to come up with a first name, a last name, a country, a city that starts with that letter. So we're going to be playing that game at 8 a.m., and there's also free coffee and cookies. And at 9, you don't want to miss the keynote by the awesome Ana Maria Porras, that she's going to be talking about her research and his trajectory in STEM. And at 10, we'll have a forum with some speakers that are going to be talking about experiences, and there's going to be the option for asking questions from the audience and some predetermined questions. What I wanted to highlight is that at the end of the day, I hope that today is just an event for celebration. I think we want to celebrate. If there's something we know how to do in Latin America, is just celebrate. So I really hope that this is just a happy occasion to be together and to share what we're passionate about, both in science and in life, in our careers. So I'm really happy to see you all here, and I'm going to pass it on. I think we are good on time, so I'm going to pass it on to Victor, who's going to be our first speaker. Thank you, Victor. Okay. Okay, I need help. From someone who knows how to use computers. So my cursor is not here.
Yeah.
Ah.
So you drag it.
Okay. Aha. Okay. So where are you here? Oh, okay. Yes, I can do that. Okay. Okay, Victor Zavala.
Yeah. Thank you. Okay, so super happy to be here. Buenas tardes. Good afternoon. So I'm Victor Zavala. I'm a faculty member in the Department of Chemical and Biological Engineering right across the street. So I'm very, very happy to be sharing, have the opportunity to share some of the work that we do in the group. I want to thank Claudia in particular for really organizing this. This is super important, and I really appreciate all the effort that you're making here. So what I want to tell you a little bit about is the work that we do in systems optimization related to plastics recycling, which I think is a topic that we are all very interested in. So, so a little bit about me. So I don't have much time, but I'm just going to tell you that I'm originally from Mexico, but I've been in the US pretty much about the same time that I spent in Mexico. So I'm kind of a weird hybrid nowadays. So I was born in the south of Mexico. So you will see down there in this dot. Right, so that's a place called Veracruz. So if you're interested in the chemical industry, that's a beautiful place to be born in. So you see a lot of chemical plants there. But my family is originally from central Mexico, which is Guanajuato. It's a little bit more scenic. It's just a beautiful town. It goes back to the 1500s. Then I came to the US to go to grad school in Pittsburgh, Carnegie Mellon, and then I spent a little bit of time in Chicago at Argonne National Lab, and then moved to Madison. So I've been here for a long time. One thing that I like to emphasize to students that identify same as me as Latinx is that being at this interface of cultures and identities is actually super rewarding. We serve as a powerful bridge between cultures and also between communities, and I think that that's super important in identifying. So that has been my personal experience. All right, so let's talk a little bit about the research problem that we're tackling. So that has to do with plastic recycling, and I'm monitoring my time. I hope you're as well, Claudia. Just a question that I always ask people, so what do you think is the per capita generation of plastic waste in the United States? So on average, and not to shame anyone, right, is on average, we all produce 146 kilograms per year of plastic waste, right? So that's about twice your weight. So that's 322 pounds per year, okay? So it's a lot of plastic waste. I'm guilty as charged, right? So my kids consume a lot of Legos, so I describe my house as a landfill of Legos. So basically that's what it is. So I'm accumulating a lot of plastic waste at home. So what is plastic recycling? A difficult problem. One of the problems is that it's a highly diversified sector. So when we talk about plastics, you're talking about a very broad spectrum of plastic products. So we use it for packaging. Every time you get an Amazon package, there's plastic in there. Building and construction, right? So just this building is full of plastic. Textiles, right? So things that we don't expect. Transportation, electrical, electronic, like our iPhones and things like that. So this plastic sector is highly diversified. And this is one of the most shocking kind of figures. Turns out that we don't recycle as much plastic as we think, right? So just to give you an idea, just in the US, 85% of all our plastic waste ends up in landfills. So it's very little amounts that we actually recycle. The reason for that is that really the only technology that we have available for recycling is mechanical recycling. And this only takes care of two types of plastics that are around. So think about your milk jugs. So that's something called high-density polyethylene. And also PET, think about your plastic bottles from water, right? So polyethylene, terephthalate. Those are the only two types of plastics that can really be recycled mechanically. So what that means is that if you cannot recycle mechanically, you have to either incinerate them, burn them, which is what they do in Europe, or landfill it, right? And the problem with landfilling, you might say, well, this is maybe a good strategy for do it. The problem is that it's not sustainable, right? So here what I'm showing in this graphic is the evolution of all the landfills in the United States over time. So you will see that there's an exponential growth in the number of landfills that we have open and that have become closed. And you see that we keep growing and growing and growing. And at some point, we're gonna run out of space, right? So you have seen WALL-E, right? The movie WALL-E, I think we're heading in that direction. So the government is very concerned about this, right? And as a result of that, they're trying to divert plastic away from the landfills. It's just simply not possible to deal with the problem that way. And this is where the chemical engineers and a lot of people associated with that, chemistry, material sciences, are coming into play. So we're trying to find new chemical recycling pathways for dealing with this. And the idea with this is to try to recover those basic chemicals that made up the plastic in some form, okay? And there are different strategies for doing that. It's a very active research area. So I'm not gonna be able to go through all of this. So I'm just gonna tell you one specific technology that is called the strap process that you see over there, that is used for recycling food packaging, multi-layer films, and I'll tell you a little bit about the story around that. Now, when you're dealing with these problems, there are a lot of ways that plastic waste impact society, right? It is impacting us from an economic standpoint. There's not an accident why we use plastics, right? It's a very effective way for us to transport, for us to store food, right? So there's a reason why we use plastics, so we need to understand that. We obviously need to understand the environmental analysis. And I'll tell you also a little bit about the social aspects of plastic. I'm gonna show you how plastic waste can create impacts that are not that obvious, like social justice and environmental justice, particularly in developed countries. I'm gonna show you, or developing countries, as I'm gonna show you in a second. So the work that we do in systems engineering, which is my area, is try to combine different types of information and data that comes from different types of levels of the problem, try to combine them in smart ways to try to inform decision-making from all these directions, economic, environmental, and social analysis. So the work that I'm just going to explain to you today is, or talk to you about today, has to do with recovery of plastics that come in the form of multi-layer films for food waste. And I want to acknowledge my postdoc, Aurora Munguia, also originally from Mexico, that has been leading this effort. So when you go to the supermarket, and we're in Wisconsin, so I'm going to use the cheese example just to make it relatable and put some skin in the game, right? So when you go into a supermarket and see your cheese store here, we tend to think that this is just like one single layer of plastic that is covering and protecting this. But in fact, this is actually a very sophisticated protection system. It's a multi-layer plastic film. These things are very, very advanced, and this is the secret of why we can store cheese over long periods of time, okay? So what happens is that we have different layers composed of different types of plastic. So for example, we have polyethylene there that serves to protect moisture, right? And also heat. We have plastics like EVOH that help protect the cheese from oxygen. So oxygen will tend to decompose the plastic, the cheese. And then we have other types of polymers like modified polyethylene and PET. PET is interesting because that attributes strength and also some of the visual aspects to the plastic component. So this is one of the reasons why we cannot recycle this. It's just a complicated waste stream that is hard to kind of separate and make sense of. So Professor George Huber, together with his student Kevin Sanchez Rivera here in the Chemical Engineering Department, they came up with a very clever idea of using solvents to selectively separate these plastic layers one by one, okay? So the idea with plastic, which is quite interesting, I did not know this, but maybe I should have known this because I'm a chemical engineer, is that if I put granulate plastic the way that you're seeing it there, okay, and then I put it in a solvent, so this solid will solubilize just like salt, right? Just the way that you solubilize salt or sugar, it will solubilize in the solvent if you select the solvent appropriately. And if you do it carefully, you can solubilize one of these layers at a time, and then you can do 3 cycles in this particular case, for example, to separate the 3 different types of plastic. How do you select the solvents? And this is where it gets super cool. Turns out that there are very advanced molecular simulation tools nowadays. For example, in the group of Reed Van Len here in the Chemical Engineering Department, they have the ability to predict what types of solvents could be useful for separating different types of plastics, and they can inform this decision-making process. So once we have this input from them, we design the process and we do techno-economic analysis. We try to figure out what are the pieces of equipment that could be involved in this process. After that, we'll do a life cycle assessment to try to determine, for example, in this process, where the energy consumption is going to, what are the key sticking points in trying to separate this plastic. And the real slide that I want to show you before Claudia kicks me out of here is this one. This one is really interesting because we have been able, through life cycle assessment, figure out a way to tell manufacturers, like companies like Amcor, that are actually based here in Wisconsin, that make this plastic waste, which one of these layers are the largest responsibles for environmental impact. So it turns out that some of these layers have more impact than others. It's not immediately obvious. You have to do very careful analysis about what they are. So just to give you some idea, in this particular analysis, we found out that this particular polymer, EVA, that you see there, the plastic, it is just 1% of the plastic layer, but it's responsible for the largest contribution of CO2 emissions that comes in the process. So this is very helpful because now we can go back to industry and tell them, you know what, this one is a troublemaker, so maybe try to consider a different approach to create this food packaging. Just to finish, we've been working on understanding some of the impacts of plastic waste from a social perspective. I come from Mexico, and this is a familiar view that you see in plastic waste. We rely a lot on waste pickers. We don't have a well-developed infrastructure for collecting plastic waste and for separating plastic waste. This introduces a lot of problems in places like Mexico and Latin America because these are people that are exploited, right? So they're paid very low wages and they have to do a lot of work, right? And they're not remunerated well. So the idea here is that we're trying to identify ways in which these new technologies for processing plastic can actually benefit society and potentially eliminate some of these societal problems. So with that, I will thank you for your attention. I'm happy to take any questions. I'll also be here during the reception. You have questions, but go ahead.
We have 1 minute for questions.
As usual, at least one. Any questions? Yeah.
So that Ava one, what is that used? What?
It's mostly a polymer. In many cases, they use it as an adhesive between the layers. So it has to be something that keeps the layers together. And in that particular case, that's the function. That's why it's so little, right? But it's the one that is really holding the whole thing, holding the sandwich together. So, yeah.
And if we want to, minimize the use of that, is there one particular product that we should avoid?
It's very complicated. So I'm going to say that food packaging is a very big enterprise, and there are a lot of products. Just to give you an idea, coffee, right? Coffee has to be protected very, very well because it has a lot of volatile molecules. That is what makes it awesome, right? So there's very complicated layers. So I think that is a complicated question. There are many different types of food packaging that we should worry about. Yeah? Okay.
Thank you, Victor. Okay, so our next speaker is going to be Mayra Oyola Merced. Thank you, Mayra.
Just so you know, I normally don't wear heels. It's not my fault. I wear it for class and for presentations, so. Okay, and I also have a timer because I have a lot of slides. So it is so nice to see you all here. I'm actually a second-year professor here at the University of Wisconsin, so really nice that I can see that I have a very strong community. My title is the Ozone, the Good, the Bad, and the Tropics, and I want to highlight the contribution of my undergrad student, Nuyte Rivera Maldonado, which is from the University of Puerto Rico, Mayagüez, and she's the one who has been working really hard with this. I am also from Puerto Rico. That's why I speak so loud and fast. So please bear with me. But I didn't mention I am from the Department of Atmospheric and Oceanic Sciences, so right across the street with the big antennas. They're not antennas, but the big dome on top. Some of my areas of research are satellite remote sensing, radiation, and atmospheric composition. So I'm going to focus on that last one, atmospheric composition. And particularly, I'm going to talk about ozone. And why ozone? We have nitrogen and oxygen in the atmosphere, that's basic science. We also have some trace gases, and ozone is one of them. You probably have heard of ozone in regards of the ozone layer, especially in the last few decades. But what I'm gonna talk today is not that kind of ozone. That's the good ozone. That's the ozone that's in the higher level of the atmosphere that's protecting us from UV rays. What I'm gonna talk about is the tropospheric ozone, which is the ozone that's below that big blob that you see over there that says ozone layer. So tropospheric ozone actually can be harmful for human health. We know that its budget is controlled by phytochemistry, transport, and weather, but we still don't know how those pieces are connected. We have an idea, but the community is moving forward to better understand how do we account for each one of those into the actual ozone budget. And what we know is that ozone is on the rise. And obviously, as I said, that has a implication for human health, among other things, especially weather formation. And the problem is that sometimes we're able to sample ozone from the surface using stations, but obviously, as you can imagine, stations are located in very specific areas of the world where people can afford it. We rely a lot on satellites, but if you are a downward-looking sensor and you are in space, if you look at that right figure, you could imagine that the first thing that you're gonna look is at that big ozone layer, which has a more concentration or order of magnitudes higher than the ozone below. So we're kind of obscure to what's happening in the troposphere. And again, I wanna make that note, good ozone, AKA ozone layer, stratospheric ozone, and then bad ozone, tropospheric ozone below. So how does it get there? There are various processes, as we know, in the atmosphere and actually in the physical world. Things move from high to low, so high pressure to low pressure, high temperature to low temperature. Same thing with high concentrations of ozone to low concentrations of ozone. So sometimes we have storms or some regional weather shifts that can move some of that upper level ozone below. So that's what we call stratospheric tropospheric ozone exchange. Surprisingly, lining, a lot of people do not know this, but lining actually emits nitrous oxide, and that's what is known as an ozone precursor. So you can have ozone in the middle layers of the atmospheres associated with what we call convection, which is heavy precipitation. And also we have sources at the surface, and a lot of this has to do with anthropogenic or pollutants or these precursors like NOx, volatile organic compounds, and others. But a big source or a big precursor is actually biomass burning. And here, maybe in the Midwest, we know this as wildfire smoke because that's what we're used to if you were here over the summer. And we had a wonderful month of June, not. But around the world, other than the United States, there are some hotspots for biomass burning, two of them particularly near Africa, near the African continent. So what we want to know is, okay, we have the source regions and we have all of these mechanisms for ozone formation, but how do we actually know what happens after things moved in their source region? And based on that, we have two major science questions that we want to answer. So first up, I mentioned the issue with satellites. Satellite data goes into weather models. So if satellite data isn't able to capture tropospheric ozone as it does, so our models actually portraying ozone in a correct way. And the second one, which is the one that I'm going to talk the most for the rest of my presentation today, is how do we account? How can we account for each one of these processes in the actual tropospheric budget? And specifically, I'm going to focus on stratospheric intrusion, regional weather patterns, which is convection, and then biomass burning. Obviously, if we go into areas where we don't have a lot of in situ or land observations, like the ocean, we are in trouble. But that's what we do then. We go to where that source that we want to sample is. So I actually got in a boat for 200 days, not all at once. But as a graduate student, I had the opportunity to participate in the Aerosols and Ocean Science Expedition, which is a series of transatlantic intensive field campaigns that have taken place for the last 15 or 16 years. There are 12 campaigns throughout that 15-year period, and a lot of that data is actually used for satellite validation, understanding of physics and meteorology and chemistry over the Atlantic Ocean. But not only we get in a boat and we start taking observations, what we need to understand is what type of observations are we using. And those are called ozone sondes, or basically what it is a big weather balloon, if you haven't seen one. Weather balloons sample pressure, temperature, and relative humidity. But these are rare. This is a very unique type of observation. I'm not going to go through the details on how the whole chemical preparation, but I can tell you it takes about 7 to 10 days to actually prepare one of these things. It's a very laborious process to actually sample the atmosphere and also launch it. So here's an example or a video of one of those launches aboard the Ron H. Brown. I think this is 4 North, 23 West, so right next to the African coast. That balloon is a 1,800 gram balloon, so it looks really large there, but as it goes all the way up to 35 or 36 kilometers in the atmosphere, it expands to the size of a house and then pops, and is attached to the sensor. And you might be able to see it here, which I had a pointer, but it's that white box, and that person holding the white box is me with short hair back in the day. So here we go. Again, we get pressure, temperature, humidity, and ozone concentration out of that. So an example of one of those many field campaigns and where we observed, I'm using data from November 2013 here. The white dots denote the locations where we launch ozone sondes. And what we see here, just as a reminder, I talked about all these different process of ozone transport and formation, and I said, well, biomass burning, we have some biomass burning hotspots around Africa. This is why we wanted to focus on that region, because the hypothesis at the time was that most of the ozone near that region was associated with transport from biomass burning. So, and it will make sense if you look at that figure below. Now, how do we use that information to identify ozone and the ozone origins in these profiles? So you gotta remember that the atmosphere is a fluid. So every time you have a fluid, you have something that can force things to move, either horizontally or vertically. So in the atmospheric science community, two of those mechanisms are called the Rossby waves, which will induce horizontal transport, and then the other one is gravity wave, which will induce vertical transport. And now if you recall that first figure that I showed with the different mechanisms, now you can start putting together the pieces as to where am I going with this. So again, how do we relate then these Rossby waves and gravity waves to ozone? Well, this is an actual profile. And when you see that profile and it's cut up to 20 kilometers, you can see some variability, some peaks and valleys in terms of that ozone. So we can call these layers, right? Or use these different layers associated with another quantity that we obtain from the soundings to understand where do they come from. Let me explain that. So for that, we apply something called the laminar analysis, and I'm glad that Brad's here because this is his baby. So actually, this came out of a paper by one of our faculty here at the University of Wisconsin. But basically, what we do is that we apply this laminar analysis to the ozone concentration profile that we obtain with our soundings, and we correlate that with something called potential temperature. And I'm not gonna go, I actually teach thermodynamics, that's undergrad thermodynamics at AOS. I'm not gonna go through what the equations are, but please believe me when I tell you, potential temperature is a parameter that allows you to understand how an air parcel moves up or down. It has that, we can prescribe that thermodynamic capability of going up and down using potential temperature. So if we correlate that concentration to potential temperature, we know something about where that air mass is coming from. So for that, we established, without going into a lot of details, that if my ozone concentration is poorly correlated to potential temperature, that's gonna be a Rossby wave generated layer. And likewise, if there's a strong correlation, then it's a gravity wave generated layer. So what? Why do we care about that? Well, most literature, including my own in 2018, prescribe, or they say, that Rossby wave mechanisms are actually the most common mechanism for ozone formation. And that is because a lot of the papers that we publish, including the one that I publish, use data over land and in the mid-latitudes. But that's not the case in the tropics. And as Angel will talk in a second, the tropics is a much different beast. So again, what we found was the opposite. So high ozone is actually, or the mechanism that actually prevails for ozone generation near the African coast is our gravity waves. And let's put that into perspective into what was happening then. So as you can see here, this figure shows the continent of Africa. That black line that's coming from the south is moving from the south into the direction of that star. That star is the ship, or where we launched the balloon. And if you notice, that goes into that blue plume or cloud that's there right in the middle of Africa, and that's actually biomass burning. However, as I told you before, a lot of this was actually associated with gravity wave activity. If we look, we see this radar-like image that's actually precipitation. This is satellite imagery or satellite data utilizing infrared and microwave sensors from NASA. And this actually explains why gravity wave, which is associated with convection or heavy precipitation, is one of the mechanisms that's actually associated with high ozone formation in that region. So we did that with 4 field campaigns. So that's about 40 different profiles out of the 250 that they have obtained over time. And we continue to look at that. But ultimately, that was the conclusion that almost 75% of the ozone-generated layers are coming from gravity wave. Now, the last thing that I wanted to mention, because it was one of the things that I said, it was our question, is what happens between the model and the observation. And if you can see here on the left, we see an actual depiction of that box that I created before in that transect north to south near the coast of Africa. This is using something called reanalysis, which is a very advanced and corrected version of a weather model. And then on the right are the corresponding observations for that. And it's very easy. You don't have to be an atmospheric scientist to know that that and this are very different, especially when you look at latitudes below 4 north. So we're actually collaborating with the National Center for Atmospheric Research in improving ozone in Musica, which is a very advanced high-resolution model that they have, with the hopes of actually being able to advance the understanding of ozone and ozone knowledge in our community. These are some of my contacts if you want to grab coffee or just talk more about my research. And again, thank you so much for having me here. I ran through that.
We don't have time for questions. So, sorry, it's a Latinx event where we are operating on German time. So the next speaker is going to be Ángel Adames Corraliza, and I need to open your slides here. Thank you, Ángel.
All right, good afternoon, buenas tardes. My name is mentioned Ángel Adames Corraliza. I'm going to talk about the tropics. So I'm following up Mayra. I think it's actually appropriate that a loud person actually follows another loud person. And I will be honest with you, I just gave a lecture like just before coming here, so the wheels are totally coming off. So hopefully you can bear with me in this talk, okay? All right, so I'm going to be talking a little bit about the history of tropical meteorology, and then I'll talk a bit about what my research group is doing and what the community is doing as a whole. And I think it's important to give this context first. So here's a geostationary satellite image from a satellite called Himawari. And I always start my talks by showing these global images because you can really see that our planet has very distinct regimes, right? You have the extratropics where Wisconsin is, where you get these motion systems that are called, mid-latitude storm systems, which have cold fronts and warm fronts, and they have a very particular appearance if you look at a satellite image. Now, if you look at the very middle of that satellite image, you'll see that there's a lot of clouds and a lot of messy-looking things. None of those things look like the stuff in the mid-latitudes, right, in the extratropics, and that's because the physical processes that occur near the equator in these tropical latitudes are actually pretty different. Now, as I mentioned earlier, there's been a lot of work done to understand the mid-latitudes features, which are these like mid-latitude storms. These are the systems that affect our daily weather. If you have a warm day and a cold day, there's usually associations with the passage of these systems, right? You usually have a warm day, these storms pass, and then you actually get a cooling weather here, right? You get a cold front that passes, and it cools the weather. So what happens is that this system that you're seeing here on the screen is actually one of the most studied weather phenomena on Earth. In fact, if you go and look for books in atmospheric dynamics or in meteorology in general, you will find that the majority, I just ripped off my sticker. So if you go and do an Amazon search for books in atmospheric dynamics or meteorology, you will find that the vast majority of books are mid-latitudes, right? Extratropics. And you'll see that the majority of books here that you see on the screens have mid-latitudes written somewhere, and that they don't. They're not saying it explicitly, but they're actually also mid-latitude books. None of these books actually cover extensively what happens in the tropics. So what is that? Another interesting feature is that these are the majority of the books. I, like Mayra, we're from Puerto Rico. We never got taught about the weather that happens in the latitudes that we lived in. All the classes that we took in the atmospheric science sequence at the University of Puerto Rico were focused on the mid latitudes, which is actually kind of strange. We're learning about a different set of latitudes and not the latitudes we're actually living in. So what about the tropics? What makes the tropics so not studied, right? You have this picture here, you have your like interesting weather systems in the mid-latitudes. You have a theory that's actually known as quasi-geostrophic theory that explains a lot of the main features. That's actually what all these textbooks that I mentioned in the last slide are about. In the tropics, you just have a question mark, right? You have all these areas that don't have a lot of clouds, and then you have these really cloudy regions right in the middle, and then you have a hurricane here and there. And what about this? What is the physics of this system? And why don't we have a lot of textbooks about this? Why is this not something that we get to study? So I like to show this map because there is a lot of information in here. So this map separates this whole free world theory, quote unquote, here. You have the first world, which is the West. You have the second world, and then you have the third world, the developing countries. Now, if you look at this map, you'll see that the vast majority of these quote unquote third world countries are all in the tropics. And you don't have to really be an expert of history to know that these are really all the countries that were victims of colonization of the West, right? These were essentially all these countries where these countries from the North came in and essentially extracted all the resources and exploited all the people that were there. And what ended up happening was that these areas were largely ignored. In fact, what's interesting is that if you see movies from like the early 20th century, they will usually have horror films, and all the horror monsters will actually be like tropical trees and tropical animals. So there was like this like mystique, but also like this fear of the tropics. And people really didn't pay much attention. As I'm going to show you later on, there was a lot of bias about what actually happened in the tropics. And actually, people from Europe and the United States didn't really think the tropics were that interesting at all until World War II happened. And that actually changed everything. And the main reason why everything changed was because the US got into a fight with Japan, and a lot of the battleground was actually in the tropical Pacific. And actually, a major Navy ship actually sank due to a typhoon passing. And all of a sudden, then, okay, now we really need to understand tropical weather so we can actually win the war. There's actually like an unspoken deep history and connection between wartime efforts and meteorology, especially tropical meteorology. We don't speak about that much, but a lot of the major advances that have happened in our field are related to wartime efforts. Now, an interesting thing is that I just mentioned that knowledge happened with World War II, but I don't want to like obviate the fact that the Taino people existed, and they were actually the main population of the Caribbean, right? If almost every Puerto Rican has some amount of Taino heritage in them. And much of the knowledge that the Taino had was lost to the Spanish invasion. And I think I show this picture here because it's like a caricatura of what the people thought Taino population was like. But the reality is that we actually lost most of the knowledge about the Taino knowledge in general. But we did know that they had a god known as Huracan. And that sounds familiar is because the name hurricane actually comes from Huracan. And of course, the Spanish name Huracan comes from Huracan. And so the thing that I want you guys to note here is the symbol, right? The symbol has bent arms like this, right? And if you actually go to the next image, you'll see that the arms actually flow around in the same way that spirals in a tropical cyclone do. It actually is very similar to the spiral rain bands that you actually see in a hurricane. And in fact, it looks really similar to the cloud patterns that you see here in this image of the typhoon. And what's remarkable about this is that, as far as we know, Taínos didn't have any satellites in space to look at the hurricanes from remote sensing instruments. So there's knowledge that the hurricane had spiral winds. They knew from experience. This was actually knowledge that they had accumulated over the centuries they had lived in the Caribbean. They knew basic physics of hurricanes. They knew how these systems worked, right? So even though that knowledge was lost, we know based on the symbol that they actually had knowledge about how hurricanes worked. Now, because this information was lost because of the Spanish invasion, we don't know anything about Taino science other than this. But they may have known a lot more about how hurricanes work than what we know right now. but it's lost to history. In fact, aside the Taino, with all that knowledge lost, then all the knowledge started getting created again with World War II. And this is an interesting textbook because this is from the first tropical meteorology book ever written and was about how people that came from the US and from Europe went to Puerto Rico, which is where, mine and I are from, and they started a school of tropical meteorology there to understand how the weather in the tropics were, to better improve wartime efforts. This school of tropical meteorology occurred in the early to mid 40s, and then the school ended. They learned a lot of things. They actually discovered a lot of things, but none of that knowledge was left in Puerto Rico. They all left, and nobody in the island even knew that this even happened. In fact, I went to the University of Puerto Rico, and nobody ever talked about this ever happening. And in the School of Tropical Meteorology, they discovered warm rain processes, which is like the processes in which you can create rain without actually having any ice included. They discovered the easterly wave and so forth. And in fact, there's an urgent demand here, this little passage from the book that I'm gonna skip here. Since then, there's been a lot of increasing efforts to understand what weather in the tropics is like. And one of these major features was the discovery of the equatorial waves. All of these are structures of waves that are horizontal structures, so this is how they would look if you look from space. There's a whole menagerie of them, so there's a big variety of waves. But all of this came with the bias that we were using dry theory, not incorporating rainfall, into understanding how these waves behave. And the reason why we did that is because we were incorporating mid-latitude thinking, because we can actually understand a lot of how the weather here works without ever invoking clouds. You can actually just think about the winds, and that works great. And it actually started working fine in the tropics until they had many, many problems in finding that, we can't get our weather forecast models to actually forecast weather in the tropics, and we can't get good climate projections in the tropics because of things that were happening, because we didn't understand the process well. So now fast forward to the 2000s and 2010s, and now we know several things a lot more. And that's also because of the increasing observations, but also the participation. The people that have started participating in this have brought different contributions. One of the things that we know about the tropics is that this is a picture of temperature. This is temperature at like 5 kilometers of elevation. And you will see that if you look in the Wisconsin, in the North America, Canada, you'll see the temperature changes very rapidly with increasing latitude. So as you go to the poles, things get really, really cold. But if you look anywhere in the tropics, you all see just red. So that means that above the surface, the temperatures in the tropics are pretty homogeneous. They don't change a lot in space and time. It's actually pretty warm all the time, right? If you live from the tropics and you come from Puerto Rico like me, that should be an obvious statement, but actually globally average, it was actually like a major discovery. And the reason why that is, and I might have hinted at this before, is because of the existence of these waves that actually transmit all this energy. So actually all this energy is in these thunderstorms that occur in these really rainy regions of the tropics. All that energy comes from the condensation of water vapor into liquid water. And then these gravity waves, which I show in the animation here, go boom. And they just expand and take all that heat and disperse it throughout the tropics. And because the tropics don't have a Coriolis force that's pretty weak, which is the amount of rotation that you experience, all that energy can effectively be transported everywhere. And that is happening all the time. Absolutely every minute, every second that you see, waves are actually transporting energy in the tropics, creating this homogenization that you see. It's like a ripple in a pond, right? And it's actually kind of weird because you think it's a ripple as like a change in the water level in the pond, but this ripple is what actually keeps the pond smooth. If you didn't have these ripples in the pond, there would be topography in your pond. The pond would actually have like little hills and stuff, right? Because it is actually these things that actually cause the pond to be smooth. And isn't it weird to think about a pond that actually has hills and stuff? That is so strange, right? So we know that even though these waves are kind of weird to think about, we know that they have to be really important because their net effect is to make everything really smooth. However, there's something in the tropics that's not smooth and creates a lot of the weather patterns that we see in a daily living, and that is the movement of water vapor. So this animation here shows what's called column integrated water vapor. So it's the amount of water vapor that you have above you if you look up to space. And if you look here, the red colors are areas where the water vapor is really high. You have almost a meter of water vapor above you that can turn into liquid water. Areas that are purple are actually areas that's pretty dry. And you see that the vast majority of water vapor occurs in the tropics. And if you look at that image there on the right, you'll see that all the clouds, all the rainfall occurs in these envelopes of high water vapor. So it only rains when it's really humid, and if it's dry, it actually doesn't rain that much. So we now know that there's a lot of weather systems that exist that are unique to the tropics. They're driven by these water vapor fluctuations. We actually call them moisture mills or moisture waves. They're similar, in another category. You got gravity waves, you got Rossby waves that you heard from the last talk, and then you have these moisture waves that are unique to the tropics. And this has actually kind of like opened up the field, because before we just thought that things were just dry. But water vapor is not dry. Water vapor is water, right? It's not dry at all. And now we know that because of water vapor being so important to the tropics, you actually have distinct physics and dynamics that do not happen anywhere else, except in the tropics. And that's actually led to numerous advances into our understanding of weather and climate in the tropics. And this is only accelerating. So, ask me next year and I'll have a different talk. So, including clouds, radiation, humidity, they're all really important to understand weather and climate. If you want to know more, you can just come and ask me, because, I'm going to be here. I'm going to, there's not going to be Latin American food, but I'm going to be pretty hungry soon. So, I'll be there munching on food, and you can come and talk to me. So, thank you.
We have 1 minute for questions.
So,
So you talked about how none of the understanding of tropical dynamics stayed in Puerto Rico. Was that because it was all classified at that point?
at that point, yeah, it did become declassified eventually, and now all that data is publicly available, but it was never really explicitly shared with anybody. So people have told me, it's yeah, you can actually find that now, but was there ever any concerted effort to come back and do outreach and teach people about all that knowledge once it became declassified? Yeah.
Thank you.
And I should have said this, if the speaker could repeat the question, if asked from the audience, just because on YouTube they cannot hear it. And I should have said that 3 talks ago. Okay, so the next speaker is Daniel Pimentel Alarcón.
Thank you, Claudia, and thank you, everybody. My talk is going to be quite different from the ones that we have seen so far, because what I do is mathematics, and they may appear somewhat dry and abstract, but hopefully today I will show you that they are really fun and easy to grasp. And I will do that with something that most of you have quite good familiarity with, which is ice creams and waffle cones. Please don't ask Victor what is the footprint that ice cream has on the planet, because then you won't be able to eat any more ice cream with a clear conscience. Thank you, Victor, for ruining that for me. Please avoid him at all costs, especially when it comes to this topic. Waffle cones, right? So I'm going to tell you about that. We have hopefully all seen waffle cones and other types of ice cream cones. There are many flavors, right? And in mathematics, we like to model everything. And that is kind of what I do. I develop mathematical models that try to, simplify the world a little bit so that we can, develop theory, understand something about it, right? Apply it to something else. In this case, we know there exist many types of cones. In mathematics, we also have several types of cones. We like to give them names. Polyhedral, convex, tangential cones, all these sorts of different types of cones. And the one that I'm going to focus on today is actually my favorite type, which is the waffle cone. And in mathematics, let's say that we want to model this cone. We want to model a cone, right? Something that holds ice cream inside. We cannot use really waffles in math. So instead of that, we use lines, right? Like this first thing that we could try is to say, okay, let's think of the border of the cone as 2 lines. Step number 1, check. But 2 lines are 2 lines a cone. What is a cone, right? Well, mathematicians, we also like to define things as precisely as we can. And here is what we come up with. This is an example of the type of thing that we define, right? And we say, okay, a cone is a subset of a vector space that is closed in linear combinations with positive coefficients. And everybody's like, what the hell, what is that? Well, in words, what that means is that if you take any 2 points in these 2 lines, the rule to be a cone is that any other point in between those 2 lines has to be also part of the cone, right? So basically, all these guys that are in between these 2 points. But not only for those 2 points, but it has to be true for any 2 given points, right? For instance, these 2, that point in between them, and any other point in between that dashed line should also be part of the cone, right? So also for these 2, and for these, all the points inside these 2 lines, and in between any 2 points in these lines should be, if they are inside whatever you have, then that thing is a cone. Does that make sense? Okay, cool. So another way to just say this, perhaps in simpler terms, is just to say, well, in all the air and all the ice cream or whatever it is that it's inside the waffle, right? So that's how mathematicians would define a cone. Now you may be thinking, well, why do we like cones? Well, they're good for containing things, right? And just the same as they contain good ice cream, they can also contain data, and that is kind of what I do, right? I try to find cones that can encapsulate data. I'll tell you later about why that is, but first let me tell you how they can be good containers, right? So they can be good containers because imagine, enumerating the list of all the points in between this waffle cone. We already agreed that there are infinitely many of such points. So it would be an endless list, and imagine storing that in a computer. That would be terribly inefficient, right? So instead of that, I could just, store in my computer the information about 2 lines, right, where they are located. And then I automatically know anything in between those 2 lines, anything in between, any 2 points in between those 2 lines should also be part of the cone, right? It's much more efficient. And for instance, in flatland, like if we think of a cone that is just those 2 lines, right? A flat cone, like the one drawn in this figure, then I would only need 2 lines to describe this cone, all the points inside this waffle cone, right? And then here is where I would like you to start thinking critically, right? So if now I live in a world like this and we're like, a real waffle cone, right? Do I need 3 lines to describe this waffle cone, or how many do I need, right? I mean, so if I think about 3 lines, I would be essentially like constructing like a cone that has like 1, 2, 3 lines. It would be like this kind of triangular cone, right? And is that kind of the same as the waffle cone? Well, I don't know about you, but most of the waffle cones that I've eaten, they're kind of like more circular, right? And what that means is that if I model my cone as just whatever is inside these 3 lines, I might run into the problem that some point, for example, this red one may not be inside my triangular cone. The same for this one, the same for that one. Even if I include, let's say, okay, well, instead of 3 lines, how about I include 3, 4, 5, 6 lines, right? One other line that touches the first red point, another line for the other red point, another one for then I could still find another point that is outside that cone, another point that is outside that cone, right? So here is a question, and let's see how your intuition works. How many lines do I really need to model a real waffle cone, like a 3-dimensional waffle cone, like the one that you all have potentially tried? Who says, well, we already agreed that 3 are not enough. Who says 10? Well, who says infinitely many? Okay, you are onto something. Who says fewer than infinitely many? No one. Okay, well, okay, yeah, okay, nice. Well, let me tell you something. All of your intuition is actually quite good, but it's also, the answer is wrong. And I'll show you why. So I said, how many lines do I need to essentially contain a waffle cone, right? And let me show you. What if I move this first line? I tilt it a little bit outside, right? And I tilt the other one a little bit outside, and I tilt the third one a little bit outside as well. So instead of having like this kind of like sharp angle cone, instead I have like this very wide cone, right? Almost like it looks more like a box, right? Like one axis, another axis, and another third axis that way, right? Like a box, like 3 lines, right? Then those 3 lines, I don't know about you, but they would definitely contain the waffle cone, right? So the answer is 3. I need 3 lines. Now the question is this, right? Okay, at this point you're like, okay, Daniel, really, is that what you investigate? Like just how many lines you need for a waffle cone? And you will be surprised, but actually the answer is yes, because Wait. The next question that I want to ask you is, okay, imagine that I give you a cloud of points, right? Imagine those blue points right there. And I ask you, okay, question number one, how many lines do I need to encapsulate those points using a cone? Well, we already agreed how many we need, like 3, for example, in the three-dimensional case. Now the next question that I want to ask you is, can you find the smallest such triangular cone, right? So we already agreed that, I can open up my axis as wide as I can, like 90 degrees, and that would encapsulate my cone. But is that the best we can do? Is that the smallest cone that I can construct, or is there a smaller one? That is the first question. The other one, is there going to be a single unique solution to this? Could it be maybe that there may be more than one smallest cones, triangular cones? And the answer is that you will be surprised, but nobody really knows the answers to these questions. It's extremely simple, and if you have ideas, like intuitive ideas about how you would solve this problem, please come and tell me, because I will be very interested to try your ideas. And you may be onto something. Please don't let this be, like overwhelming in the sense that, nobody knows. How could I potentially figure it out? Well, also, not a lot of people are investigating these things. So maybe that's the reason why nobody knows. So what I am trying to do is trying to find out these types of questions, right? Investigate these types of questions. How do I do it? I come up with, some funny math, but essentially what I do is try to say, okay, well, how can I say in math words, or something that is very, clear and precise? How can I say I will make my waffle cone wider, right? Or how I say those things? That's essentially what I do, right? Come up with the math to say the air and the ice cream inside the waffle cone. I just come up with other ways to make that a little more precise, and try to come up with algorithms and theory that tells you, oh, if your cloud of points has these or that characteristics, then the best waffle cone that you may find has these or that angle, or there are going to be more than one, or there are going to be how many. And actually, well, the answer is really still nobody knows most of these questions. At this point, you may be, let me see, how am I on time? I'm good on time. So you may be wondering, well, okay, well, this all sounds great, but because Victor already ruined ice cream for you, why do you even care about waffle cones? Well, it turns out that cones tell us a lot about the data. So sometimes, as I said, you can summarize big amounts of data using just a few cleverly selected lines or vectors or points. And these type of the application, I can this is where the application of my theory, it could take me about 30 minutes to explain you how these really actually relate to real world applications. But just trust me for now that it has lots of applications in the world. One example is single cell sequencing, right? Sometimes you want to think of. Let me not get into the details of that because I won't have time. But trust me, if you are curious about how this applies to single cell sequencing, come talk to me in a little bit during the reception. It also applies to recommender systems. It applies to image processing. It applies to really these problems. In a way, they're really fundamental, and so they apply to a lot of what we do in data science. And this is really all I have. And so thank you all. And if you want to know more about any of these topics, also if you like math, or if you like cones, or if you like ice creams, or especially if you have any ideas about how you can find the smallest cone that contains a cloud of points, please come talk to me during the reception, or shoot me an email. This is my address. Yes, the question is, what inspired me to study this type of research? You mean applied math? Is that... Oh, specifically cones. Oh, okay. So, well, math, I've always liked math, and I think that it's really, really fun. Specifically the cones, it turns out that I found one application, which was single cell sequencing. And it turns out that that people have been solving this in many ways. And I realized when I was, learning about this, that cones are one way that can be used to solve this. And then, then I went into the rabbit hole, and then I was like, I don't even care anymore about single cell sequencing. It's more about just the math. It becomes really beautiful.
When you say it's impossible to find the smallest cone, are we talking about any data points? So let's say we have 10 data points. We know that data point. Are we still not able to find the smallest?
All right, so that's an excellent question. So I'll repeat it. The question is it in general, is it impossible to find the cone for any given cloud of points? And so let me clarify, it is not impossible. So somebody gives you a specific, like say 10 points, right? You maybe can find one cone that contains it. You may not be able to find the smallest cone that contains it. You may not be able to know if the smallest cone that you found is even the only smallest cone that there exists. So it depends a lot on the location of these cloud of points. It depends on many things, on the dimension of where these points live, right? It depends on a lot of things. And the answer is, in general, it may be possible to find some of these cones. There are algorithms for that, and there are some specific conditions under these algorithms will work. But in general, really nobody will know how to find this cone, or under which conditions you may find the cone. Mm-hmm.
Thank you, Daniel.
All right.
Okay, so we're getting closer to the end. We have 2 more talks, and okay, so our next speaker is Lucia Gutierrez.
Thank you, Claudia, and thank you all for being here. This is going to be very, very different if you thought math was going to be different. And I have many slides, so bear with me. I'm going to go on an overview, get you to some of the points, and especially talk about some of the things that people in my group have been working on. And this is going to be on genomic selection in cereals. So we're going to be talking about plants and genetics and how do we get better crops to eat. And breeding 100 years ago was something like this. So this is when modern corn breeding started in the US, and this was in Iowa. And since then, you can see on the right, the yield has increased a lot. And that was mainly breeding, but also agronomics that made the production higher. And usually in a world where we have, a growing population, and we have many more challenges, we need to think about how are we going to improve the food availability. And it's not just production, it's also distribution, but we do need to compensate and have more food. And so we have the growing population. We also have climatic events, and we're going to have more with the climate change. We're going to have more extremes and more unpredictable weather. We also need to have, and people are demanding more nutritious food, not just any type of food. And we need to provide for the livelihood of the farmers who produce the food. And so all of these are new challenges that we have. And for that, we need to think about breeding and improving these crops that can serve this cropping system performance. And that means not just one single trait, like maybe yield was the case 100 years ago, but we need to think about many other traits. And that is ecosystem services. It also means the profitability. It also means health and nutritious food and stability and resilience to climate change. So we need many, many more metrics. So how do we get there? So we have multiple targets. We have some of those that are moving targets, and we need to see how to get there. And there is some theory. I work in quantitative genetics, so I'm going to show a few equations, but we're not going to go into the details. But basically, what we have done is we start with a population, the one on the top, and we select the best ones, those dashes and lines there. And then we intermate, we cross the individuals, and then hopefully we make progress. And to make that progress, we need that whatever we are selecting as the best are truly the best. And that means genetically the best, and not just environment noise making noise and not letting us progress. So that's my breeder's equation there. That's the response to selection is a function of, how much do we push that equation to the right? And that's intensity. How accurate are we at evaluating the true genetic value of an individual versus noise, right? And that's the R. And then how much diversity do we have? How much variance do we have? And that's a sigma A there. And then how long does it take us to complete a full cycle? And that's the time. So that's my background on, I'm gonna tell you about a few things we have done in my group to impact that and to make it more efficient. And this is just a general picture. What we do is usually we spend a lot of time on, selecting the individuals, making crosses, evaluating them, and then again, we select, we make crosses, we evaluate them. And this, humans have done it for 10,000 years, and we keep doing it to have better crops. So things that we have done in my group to help in this and to optimize this breeding systems is we have worked with the time. That T on that equation, remember, if we can do it faster, then we can make more progress in the same amount of time. So one of the things is working with speed breeding. And this is just, pushing the plants to flower earlier and to have a cycle that is gonna be shorter. And we have done is optimize that for oat, how much light and how much temperature do we need to put there so that the plants will go to flower faster in the greenhouse, not in general, but in the greenhouse so that we can have more cycles and do more selection. And this is the work that two people in my group, Pablo Gonzalez and Amanda Bata, have worked on. And we have gone from 111 days to 79 days in oats, which is a lot. It means that we, instead of doing 3 cycles a year, we can do 5. Other things that we have done is we have worked on selecting the crosses. How do we cross and how do we choose which ones do we cross? And we can do that with genomic information. If we have marker information, if we have genomic information, we can select complementarity. This means that when we make a cross, that cross is going to produce a progeny that is going to be more diverse. And if it's more diverse, we have higher chances of finding truly better individuals on this curve over here. We have also worked on simulation to try to see if we lose diversity by going so fast. And by controlling for diversity, making sure we don't lose diversity when we do these fast cycles, we have shown that our genomic selection, the red ones over there, we can still keep making process after many generations. So this works. It's a good strategy as long as we control for the diversity. Other things we have worked on is in this, we use mathematical models with some models to train our data. So we have genotypic information. We also we evaluate the plants, and we have the traits, for example, grain quality. And what we want to do is predict the performance of individuals that we haven't seen yet. And that's what's called the genomic prediction. So we have worked on optimizing our training population. This is the work of another PhD student, Ines Berro, in my group. And she has worked on optimizing that, and that's going to the accuracy on how well are we at evaluating the true genetic value of those individuals so that we can select. But, this, okay, this is a weird looking slide. So my plants there, those are barleys. I work with the cereals. I love the barley. We have 2 individuals there, and they are different. And they are different because they are different genotypes. So the genetic is different. But also the phenotype, what we observe, which is the grain quality, or maybe the malting quality in the case of barley to make beer, or the grain yield, is influenced by the environment. So we also have an environmental effect. But one thing that is very peculiar is that there is also an interaction between the genotype and the environment. So the same genotypes, we put them in 2 different environments, and maybe the best one is going to be different depending on the environment. That makes it challenging to select for, and that means that when we think about breeding, we're not going to have just one genotype that is going to be best for, the whole US. We will need to start to think about a specific and targeted selection. So that environmental variation, we have classified into things. One is what's called the microenvironment, and this is at small scales. And then the other one is the macro environment, which is at big scales. So locations and years. And so my group has been also studying how this G by E or genotype by environment interaction works. And this is the work of Bettina Lado. And she has been working on a very large data set in wheat. This is more than 1,400 individuals in more than 35 environments. She's been evaluating how is this interaction and how can we select for local adaptation. And we have extended that to oats in the Midwest. So that work was in Uruguay. This is oats in the Midwest, and it's another PhD student, Pablo Sandro. And what we are working on is trying to find these groups of environments that are going to have similar rankings, so that when we select the best genotypes, we can be sure that they are going to perform well within those groups. So there's not going to be that much G by E. And what we have done with that is we put those models into what's called the farmer's variety decision tool. And this is if the farmers go with their zip code data, they enter their location, and then we give them the prediction of what is going to be the best cultivar or best genotype for their location, so that then they can grow the varieties that are going to be optimized or best for their locations. And again, this is with large data sets, and I'd be happy to discuss any of those models during the time of the reception. But then, the environment is very complex. So trying to add more layers is also kind of complex. So what we have done is we have added layers to this genotype by environment interaction to try to understand and predict the performance of the genotypes a little bit better. And so for that, we have used PLS regression, and a lot of other statistical components. But basically what we have done is trying to understand which environmental covariates are more important to this interaction between my genotypes and the environment, and also to include them in my model so that I can increase my predictive ability. So here I'm increasing my predictive ability by using this environmental covariates. This is a work by a PhD student, Eliana Monteverde, and then in rice, and that one is in wheat. And another, she was a master's student, and that's Ina Rebojo. So trying to understand this, including the environmental covariates so that we can predict that better. The other things we have worked on is experimental design optimization. In breeding, we spend billions of dollars every year in testing, in evaluating the genotypes. And that means we put them in the field, we actually do field work, we put them in the field, we evaluate them in experiments, in large experiments, and we do that in multiple locations so that we have an idea of this local adaptation. And we spent billions of dollars. And so have worked on optimizing experimental designs for these large genomic data sets. And this is a work of different people. The top one is a wheat work, and that was Alejandra Borges working on the optimization of experimental designs. And then in wheat, and then another group, Pablo Gonzalez and Luis Diaz working on oats to try to optimize that. The first one was in Uruguay, this one was in the Midwest. And then we have created new designs that are optimized, and that when we put them in the breeder's equation up there, we produce a 46 more higher response to selection than classical methods. That's a lot. The average increase in response to selection for any crop is maximum 7-10%. So this is a lot of gain that we can have by having this more clever, thoughtful experimental designs. We have optimized this to try to find optimums on how much replication do we need and how do we allocate these resources. And this is the work of another PhD student, and that's Regan Heffler. And we have also worked on, do we need all the locations? When we do the testing, we spent billions of dollars, I told you, but do we actually need all of them? So we have worked on optimizing those locations, and that was a postdoc, Jeff Nehart, working on that. Then to the other cool stuff is we have worked on sustainable cropping systems. And so we have worked on resilience, and I'm going to go quite fast because Claudia is already there. So resilience and stability. We have also worked on, can we breed for a good microbiome? We know the host is very important in recruiting the microbial community. Can we actually breed for that at the oat level, right? So that we'll have better communities in the soil. And can we use that to design better cropping systems? And this is the work in collaboration with plant pathology group. And then we have used, I told you, we need many, many traits. We need to think about many more things at the same time. We have worked on multiple trait prediction to try to get at all of those at the same time. And using genomic prediction, we have increased the predictive ability. And then working on efficiency of few traits. This is for panicle architecture in nodes. And grain size distribution that causes a lot of problems in industry because we have these two peaks that cause problems in the grain size distribution. Trying to breed for more uniform there would help. So with that, this is my summary slide. I love the breeders equation. I'm a quantitative geneticist. But we have worked in my group on trying to, at different levels of this equation, trying to make it more efficient. Some has to do with time, other with diversity, the other one with the accuracy of the genomic evaluations. We have also worked at multiple genotype by environment interaction and then multiple traits, and then finally on increasing the intensity of selection. And with that, I'll be happy to take questions if there's some. Yeah, so the question was, how do you put climate change in all your genotype by environment interaction models? And that's a really great question, and I think everyone is thinking about the same on how on earth do we put it. But one of the things that we can do is when we have the environmental covariates, we can model for any past year, and we can predict the performance for any past year, but we can also predict the performance for any eventual year, right? So we can think about what are those patterns. We know in different regions, or we have predictions of what's going to happen in different regions, right? In some cases, it's going to be more extreme events, right? So more heavy rain and floods, and or higher temperatures in odd times like this week, or things like that. And so we can put those, as we use environmental covariates, we can put those into the models to do that. But the other thing is we're also trying to predict stability. And if we can predict year-to-year stability, we can improve on that. And what we had is there was a short story about a variety that was produced in Wisconsin that the farmers loved it, and we couldn't replace it. And it was not good. It was middle of the pack. We didn't know what was going on. And I kept asking, and they couldn't tell me what it was, but they liked it. And eventually started to look at the stability, and year-to-year stability was really good for that variety. And so eventually what I found is another variety that was better performing. It didn't have disease, so much disease pressure. It was disease-free. And then it was higher yielding and better quality, but that was equally stable, and they loved it. So I think that those are also opportunities to breed for more stable in that sense. It's not going to be stable we're not going to be able to grow it in the whole US, but for specific locations, we can do that. Okay, thank you.
Okay, thank you. So we are one talk away from the food and the music. And the last speaker is actually on Zoom. So hopefully everything will be okay. So, okay. John, do I use computer audio in my computer or no? Sorry, I should. We went through this before. Okay, I think yes. Okay. Okay. Yes. So that's the speaker. Gonna give her permission to share. Okay, Ale, can you
Hi, everyone.
say something? Yeah.
Yeah, hi. Can you hear me?
Yes, we can hear you. Can you share your
Awesome.
screen?
Yes. Can you see it?
Yes. Do you think the sound is okay,
Awesome.
John? Okay. Do we do something else? to make that. Oh. Should we make this maybe bigger so that we see Alejandra a little better? Okay, good. Okay. Yeah, like
Great.
whenever you're ready. Oh, Alejandra Quintos is the
Okay,
last
great.
speaker.
Thank you. Well, first of all, thanks, Claudia, for organizing this and for the invite. I'm sorry I'm not there. I'm actually in Mexico, so it's great that this is celebrating Latinx voices in STEM. I'm in Mexico. I'm a visiting professor this year at UNAM. And a little bit about myself, I'm a second year tenure track assistant professor in the Department of Statistics. And today I'm gonna talk to you about a project that I started when I was doing my PhD, which is using mathematics to help impoverished women. So I'm gonna try to avoid as much as possible to use math, and this is gonna be more of a like overview of what I did. So hopefully it is somewhat clear. We'll see. So I should say that this is based on with my PhD advisor, Professor Philip Rotter at Columbia University. So with that, let me start. So first, a brief overview about microfinance. Microfinance studies the lending mechanism to people without access to the traditional credit systems. So these are people that are really poor and they don't have collateral. What is collateral? So for example, when you go to a pawn shop, you give your watch or your car or something as a proof that you're gonna repay whatever money you take out. But these poor people, of course, they don't have anything to give you as a guarantee that they are gonna pay you back. And so whoever is lending the money, they know they have little to no recovery in case of default. So if the group or the people default, then the lender is not gonna recover the money. So this is interesting because in math finance, we model, I should say that my specialty in what I do is math finance. I do apply probability to math finance. So the thing in math finance is that we need information about whoever is taking the money, right? And if we don't have this information, then everything becomes way more complicated. But well, long story short, this guy, Muhammad Yunus, who won the Nobel Peace Prize, and it's really topical now because the Nobel Prizes are being given nowadays. So anyways, this Muhammad Yunus in the Grameen Bank in Bangladesh came up with the idea of group lending. So what is group lending? Which is specifically in which I'm gonna focus on in this microfinance business. So a group loan, it's a loan that is issued by one lender to all members in the group. And there's a mechanism that is known as contingent renewal, in which if one individual, one member of the group defaults, then the whole group defaults. So if one member of the group stops paying her share, I should say that these loans are usually given to women so that they can provide resources for their family. And so if one member of this group fails to fulfill their payment, then the whole group falls into default and they lose access to future credits. So this mechanism is thought to incentivize, like, why is it useful? Why is group lending useful? Because, okay, you don't know anything about the people that you are giving the money to, but they know themselves because they know each other. They are part of the same village, they are part of the same community. So this group lending mechanism will induce what is known as peer selection. So that you are not gonna join with someone who you know it's not gonna pay back because that's not in your best interest. It's also gonna generate peer pressure because, well, like it's in everyone's interest that everyone keeps paying their part of the loan because otherwise they will lose access to the credits in the future. And this also induces peer monitoring. So they are gonna be checking themselves. And so then we can say in a way that the risk is transferred from the lender to the whole group in itself. And this mechanism is thought to maximize the repayment rate. So what did I do in my research specifically? Well, I'm talking about a group, but I never said what is the group size, right? And it makes sense to think that we need to determine an optimal group size. And by optimal, like it's in math or in applied math, when we say optimal or the best, like we have to be more specific about what we mean. For me, optimal is group size, is that group size that maximizes the probability of no default of the group. Okay. With that, let me tell you a little bit about the model, but first some caveats. So in my model, there is a fixed loan size, and I should say that we don't want to maximize the profits of the lender. The whole point is to maximize the probability of no default, because we don't care, usually in math finance, you care about the profits, but because these loans are intended to help people and not to make profit out of them, like we don't care about the profit. And another thing, really important assumption, is that I'm considering the members of a group to be an homogeneous collection. And you'll see in the next slide when I talk about it with the math, where is that assumption takes place. So now I think this is a slide that has more math, hopefully, but let us walk together through it. So this is the model to find the optimal group size, which I'm gonna denote as K star later on. But my assumption are that first, that for fixed K, so for a fixed group size, the group members are IIT. If you have taken an intro class to probability and statistics, hopefully this IIT rings a bell to you, but it means just independent and identically distributed. So there are two parts to it. One is that the people in the group behave similarly. That's what I was saying before, that they are homogeneous. That's the identically distributed. And they are independent because the behavior of one will not affect the behavior of the others. And this is an assumption that is convenient to make mathematically, because then everything is more tractable. And then the second assumption is that the probability of no default of one person, which I'm gonna denote as the probability that depends on K, because it depends on the group size, of no default, that's why the n, of the I person, depends on the group size. That's why I'm writing the subscript K. And I should say that all the, if I write NI or N1 or N2, they are all the same because of my identically distributed assumption. And also, so that I don't have trivial results, I need to assume that this probability of no default is strictly positive, so it's not zero. Okay, now in the next line, I'm gonna do the mechanism of contingent renewal. How am I gonna represent that mathematically? So remember that when I introduced this concept, I said that, okay, contingent renewal means that if any member of the group defaults, then the whole group defaults. So then I have this here, which I didn't write, but I'm telling you this calligraphic N means the probability of no default of a group of size K. And then, so because of this assumption of contingent renewal, having a group that did not default means that all the individuals did not default by themselves. So that's why here I write the intersection. Like basically I'm saying like, okay, you have that your group didn't default. So that means that none of the people defaulted. So that's why I have person number one didn't default, person number two didn't default, all the way to person number K didn't default. And then here is where I use the assumption that they are independent, because it's great. Like this is how I can represent, just trust me. If you remember your stats or probability classes, probably you know why this comes out, but if not, just trust me that this equality is true. And then, okay, here is the part where like we realize that something interesting was happening. So this probability, one of the properties of a probability is that it's between 0 and 1. So if you take your calculator and you start saying like 0.5, and then you square that, so 0.5 times 0.5, you are gonna get 0.25. And if then you square it again, so you multiply again by 0.5, you're gonna keep getting a smaller and a smaller number. So what I'm saying is, because this probability here is smaller than 1, every time that we increase this K, the probability decreases. So what we realize is that if we wanted to find an optimal group size, so think about like, okay, a group size that makes that maximizes this probability, we need to make this function decreasing. And I'll explain that about that in the next slide. But the whole point of what I'm trying to do here is to find this K star, in this K here, that maximizes this probability, because that is the probability of no default of the group. Okay. And then in this slide, I copy paste the last parts of the previous slide. So here we were here, right? Find the K star to maximize the probability. So I need to find this function phi that I needed to decrease with K. So because I know that this whole thing decreases with K, so I need the inside to increase with K, and because of the minus, I need this guy to decrease with K. And then the question becomes like, at what speed? I need to find the right speed so that this is indeed maximized at a certain K. And just trust me that we have a theorem that answers this question. I don't want to go through the details of the theorem because that would take me more time. But maybe what I wanted to do with this is to show you a bit of how you can use math to hopefully help people. Like we created this model that we hope, and well, actually, let me tell you a bit more about the story. Then in the paper that I'm not like sharing all the details with you here, we managed to find this function that satisfy what Muhammad Yunus proposed. He has a book. In his book, he says that the optimal group size is 5, but he never showed why. And so our goal was to find a way in which we would argue that this 5 was indeed the optimal group size. And well, let me end by saying that, as I was hinting, there are two opposing forces when the group size increases. So on the one hand, we want to increase the probability of default, because as the group size increases, the responsibility of each individual is dispersed. So think about what I was saying about the peer pressure. If I have more people, then the peer pressure diminishes, the same as the peer monitoring, because there are just more people that need to be monitored. And so mathematically, we represent this as there are more independent chances of failure. And then on the other hand, the other opposing force is that when we increase the group size, the probability of no default also increases. And this is because, well, if there's more people, then they have more collective resources. And this is captured by our function phi-k. And with that, I want to end. Thank you. Muchas gracias. Here's my contact info if you want to keep chatting about math and like about modeling things with math. I'm all ears. Thank you.
We have 1 minute for questions for Ale. Okay, Ale, I don't think there are any questions, but oh, there is one question. Oh, so they want to know what was the number. What was K, the optimal K?
It depends on the function that you choose here for phi-k, but we managed to find a function that will give you the optimal group size to be 5, which is what Muhammad Yunus proposed it to be.
Okay, yeah, 5. This is a small number. So we can ask for how many loans here. Okay. Thank you, Ale. Thank you so much.
Thank you.
Yep.
See ya.
I'm gonna end this here, and just bear with me 1 second. I know we are looking at the food. Oh shoot, where is my cursor? I lost it again. Oh, right here. Okay, so well, let's give another applause to all the speakers. Thank you so much for participating. I think that just by random chance, they are like very diverse topics. So I hope everybody got something interesting and learned something interesting out of them. As a reminder, tomorrow at 8 a.m., we'll have coffee and cookies and a game. And then at 9, we have the keynote and then a forum. And today, we're just ending the talks and we'll have some food. Please check out the posters that we have here from grad students, postdocs, that identify as Latinos, Latinas, Latines. And I'm also gonna put the music right now. Well, not right now, I'll put it in a second. But I just wanted to thank you again for participating. It's lovely to see you all here. So thank you. Okay. Okay, so please feel free to eat.